You can tell I'm not in marketing. I don't try to sell you Confluent. I'm just trying to talk a little bit about the project I've been working on and off. So the title of this talk is Using Infrastructure as Code for a Streaming Project. I'll explain what I mean by infrastructure as code, which you all should be familiar with, and to explain to you also what the streaming project is, which you also should be familiar with. Who of you does not know Kafka? Everyone knows Kafka? There will be a test. So better wake up. Okay, good, excellent. Confluent? Are you aware of Confluent? Someone shaking hand? Okay. I'll explain what Confluent is. Anyway, my name is Sven Erik, which you probably can't pronounce because K and N together doesn't work very well in English. So I started in 2018 at Confluent as a solution architect, and I'm now officially a technical trainer mostly for partners. Among other things, I'm responsible for bootcamps. What's a bootcamp? Well, if you hear the word bootcamp, you might think like this, you might have been through one of these. I have not. That's not what I meant in mind when I say bootcamp. This is closer. Tough Mudder. I'll throw you in the deep end and see how you come out the other side. That's roughly what it is. You learn a lot by it and hopefully have a lot of fun doing it. I've been building these bootcamps for quite a while, mostly for infrastructure building, but I'm currently building one for actually streaming projects. And for that, I'll get to the agenda we're going to talk about. A streams bootcamp, this is on my to-do list for quite a while, which is also we're going to use for that, and the rest comes by itself. Okay, streams bootcamp, why? Well, what is a stream? A stream is processing data. Think of it as an endless tape of data coming through your machinery, and you do some processing with it. Not quite like a Turing machine because it only goes in one direction, and it is immutable. There are lots of different technologies how to do this with streams. What kind of streams you can build? You can build them using, in Kafka, for example, Kafka streams. Kafka streams is a Java library that is open source, part of the Kafka project. If you like to program in Java or in Scala, you can simply go off and build your own applications around it. And then you will find out that things like a Hello World program that just dumps some data out on the screen is very easy. And as soon as you try to do some real stuff with it, you encounter a few problems along the line. Dealing with these problems, encountering them, recognizing where the problems are, building things around it is the target of a streams bootcamp. Now it turns out that it's KSQL. What is KSQL? KSQL was a tool built by Confluent that sits on top of the Kafka stream library. It's for those kind of people who say, what is this Java thing? I don't do Java, I do Python or C# or something like that. Or maybe I just write SQL, I just want to try to process some data, leave me alone with programming. So KSQL is built on top of that with a SQL-like language to write some stuff. You're going to see a little bit of code coming up a little bit later. Confluent built KSQL themselves and published it, mostly for their own tools, and have it available as an open source project. It's a community project, so you can download the source code and look at it, but you can't sell it on. But we recently, if you followed news, have acquired a Flink company, and we're now not just the Kafka company anymore, but also a Flink company. So we're shifting everything slowly towards Flink. Hence, KSQL here is taking a bit of backwater, and I'll explain a few bits and pieces around that as I'm trying to convert my project. So Flink, the next thing. Fine. What I'm trying to do, I'm trying to dump a bunch of students into a room, ideally, or online, and give them something to do for a week. For that, I have to build infrastructure or put up infrastructure to actually give them something to do. The infrastructure is supposed to look like this. Lots of unknowns in here. Let me explain a little bit around it. We have a Confluent Cloud. Why Confluent Cloud and what a Confluent Cloud is, I explain in a second. In there is a thing called an organization, a bootcamp organization, which I run, and then there is an environment that runs my Kafka cluster. So that's where the Kafka cluster sits that I want to use for that bootcamp. It uses the schema registry as well, which keeps track of the schema. Kafka, as you know, is schema-less. We have some data sources coming in, potentially via connectors or something like that, and then our application is supposed to talk to this. So it's independent of whatever kind of technology you use in order to get the data out. And then process something with it. You can learn Kafka streams, you can learn Flink, you can learn KSQL with that. It's just a topic, it has data in it and your schema defined on top of that. So that's the plan. Fine. What shall we use as a data source? One of the problems you have with these kind of things is, well, a stream is an endless provision of data, data coming in, whatever. Bank details, bank movements, or credit card movements, or sensor data coming in, or something like that. Endless data flowing in through sensors, through people typing stuff in, to movement of cars and so on. What I'm going to use in order to teach this? Well, I could make data up myself. There is a data gen connector built into Kafka that allows you to generate stuff. These things are highly predictable. They have a very small data set typically in there. They have a few fields in that. Reference integrity between different bits and pieces is difficult. And it's slow and predictable in coming in data. So you learn the mechanics. You don't learn anything else from it. Fine. I can write my own producer. Yeah, I have learned this of the many years I've worked at Confluent, how to write my own producers. When I write producers, I know how to tune them. I can swamp a system very, very quickly and efficiently. You won't be able to process the data coming out of that easily, that quickly. It's a data, again, it's predictable, making it very hard to just dump arbitrary data in it. What I need is a real data source, something that has real life data in it that is halfway relatable, interesting. Now in the past we used something like Twitter, whatever it's called these days, in order to get data out. Now, there are two problems with that. A, I don't like them, and B, that's not a political statement, just a statement of fact, and B, they have put a paywall up, and I'm not paying for that. So Twitter's out of the question, or X or whatever, must have a paywall. So what do I use? Well, we are in Britain. Turns out Network Rail is still around. Network Rail publishes every single movement of every single train out there in the whole country. Freely available. All you have to do is get yourself an account, which you can get for free, and then you can get all the data out. All movements of trains. Position of trains around, the schedule, all the metadata behind it, like locations and so on, is all available in there. And it's available in a so-called STOMP format, simple text-oriented messaging protocol. But it's also available in ActiveMQ. And for ActiveMQ, that's very handy. We have a ready-made connector. All you have to do is plug it in, and now it streams data. Good. Two data feeds I'm interested in. Data feed number one, movement of trains. Now they are split off by the different companies. As you know, British Rail was broken down into lots of tiny little companies. So these are called TOCs, train operating companies. And the data feed is actually split up across these companies. So you could go specialize only for, what about the Pennines train company or something like that, or Southeast Rail. But if you get to the all, then you get all the data coming in, and that produces around 10 kilobytes a second, which is kind of what I aimed for while getting this project to run. In addition to that, I can get the TD, the train describer data out as well. Train describer data actually tells you where the train is at that very moment. It breaks it down into so-called berths. Are you aware what the berth is? There's nothing going on. Fantastic. A berth is a space between two signals. If you have more than one train in a berth, you read about it in the paper next day because there has been a crash. So that berth defines exactly where the train is. Do a reasonable resolution between two signals, whatever the distance is, 500 meters or something like that. And it tells me the signal state as well. I can use this to follow exactly through where the train is going. And I actually use this at home. I live in a tiny little village called Bramley in Hampshire, and we have automatic gates going on. And when the gates are down, they're more down than they're up. Then I can use this information here to find out where the trains are, which trains I'm waiting for, and how long I have to wait for them, because I can see them coming in with that kind of like that. Now this movement data specifically, there are different types in there. Train activation, we'll get in a second. Train movement, that's the one we're after. Train cancellation, we try to avoid. as much as you can. Sometimes when things cancel, they get reinstated again. And the other ones are internal data that you very rarely encounter. So these things are all dumped into one single place, which makes a lot of fun in the moment. Good. Now, where am I going to put all this? Right from the start, I defined that in this bootcamp, I want to not bring up any additional resources. I don't want to do anything by hand. I want to point it over there, fire and forget, set it up, it should run. That's what we are trying to achieve here, okay? Confluent Cloud is a ideal place for that because I don't have to spin up a cluster, it's there already. All I have to do is say, give the thing a name, and then there's a cluster. So, that one single bit of marketing in here. What's Confluent Cloud? Well, it's Kafka ready-made there for you. Comes two different types. Shared clusters and dedicated clusters. Shared clusters broken down into basic, standard, and enterprise for various reasons, sizes, SLAs, and so on. And if you ever spun up a cluster, Kafka cluster yourself, somewhere, going through all the process of Ansible and God knows what you bring up with that, and then you go to the Confluent Cloud and say, give me a cluster of that size, and it goes Clark and it's there. Something special must have going on with that. Not quite true if you do a dedicated cluster, because in that case it actually has to be spun up for you, and that might take a few hours. Now, luckily for us, we don't need that kind of thing. We only need a basic cluster. I'm not going to go into too much detail of this, except it runs in the three major cloud providers, AWS, GCP, and Azure. You can simply point it and set, run it there. It runs in almost every single region out there in the world. And if there's any other region that comes up or you need it, then just let us know. I think the last time bringing the whole region online took 1 hour. 1 hour for everything. You don't know how much infrastructure has to be built behind that. Kubernetes be thanked for that kind of thing. Good. As resources, I need a standard cluster. Just spin up in a single availability zone. If you're aware of what that is, it's one single data center. I could run it over three, very simply. It's simply a switch I have to put in there, but one is enough and it's cheaper. I'm going to use RBAC, role-based access control, for the authorization. I follow the principle of least privilege. So any service and something like that has exactly the position, precisely the permissions to access that data topic in there that it needs and nothing else. Because I like to teach people how to make things secure as well. It needs to be in a region that supports Flink for the future. Certainly we're going to do Flink stuff in that. Fortunately, Flink is coming more and more online on every single region as well. I need a essential stream governance package, what that is in a moment. A bunch of connectors, and then currently I'm using KSQL DB in order to process all the data, or pre-process the data, and you'll see in a moment why. So my requirements are infrastructure as code, one single script written in Terraform, and no external dependencies. So I don't want to spin up another Kubernetes cluster or bring up AWS instances or do something in consumer somewhere on my local machine, because those kind of stuff is tedious. I've done this many times. Now it's not stable in any shape or form. Right, how do we do this? The answer is a Terraform provider. You're familiar with Terraform? Who is not familiar with Terraform? Come on, out yourself. Everyone. Wow, fantastic. So you know Terraform can be used to bring up infrastructure. That's what we use to bring up things on AWS or GCP or something else, but it also can be used for anything else. I recently learned how to use it to bring up a Keycloak cluster, for example, or provision a Keycloak cluster. Whatever speaks an REST API is an ideal candidate for a Terraform provider. The Terraform provider is the thing you plug in, because Terraform by itself is stupid. It can't do anything, but it needs the providers to be able to do something like that. In Confluent Cloud, the Terraform provider that we provide can do everything. It can create the clusters, it can create the topics, it can create the permissions on top of that. It can spin up connectors. It can even upload new connectors, as we will need that in a moment. So that thing is constantly evolving. I can barely keep up with the latest changes in there, and sometimes they are breaking. This is a pain. But provisionally, typically, you can use the older versions for a while on. But if you try to keep up to date, you have to change it almost every week. It's almost as bad as AWS. All right. a core example of what this looks like. So you know HCL or HCL2, this is the HashiCorp command language in which Terraform writes and writes the stuff, which is a godsend if you deal with YAML a lot of times. So I declare the Confluent environment. This is the actually latest version, 2.9.0, checked this morning. I need to identify myself somehow with an API key and API secret. Then I'll spin up an environment, and then I'll spin up a cluster. And it's there. That's all I need. It's very simple. The only thing you need to inject into here is the API key. If you ever do this yourself, do me a favor, do not put the API key into your code directly. And if you do, do not publish on GitHub. If you look through the GitHub and you look for Terraform code for this kind of stuff, you find lots of API keys in there. That's your golden key that gets you into the cluster and does all kinds of magic on it. Don't do that. The right way to do this is to put the API key and secret into an environment variable. And if you know dir env, that makes life very, very simple. You cd that directory, Terraform apply, it picks up the right environment variables, job done. Good. Okay, we have a cluster. And now, well, we need to get the data from somewhere. Well, there was this active MQ thing. Can I put a connector in place? Oh, look, I can access the connector using Terraform. Well, that's handy. Well, in that case, let me configure a connector, point it to the right places in the right cluster. We provide the correct password as well as data and some information of where you're going to pull data off. Point it to a topic and said, give me. And seconds later, it starts to run up and then dump data into that topic. And it will do so ad infinitum. As I said, I need to get permissions in place following the principle of least privilege. Right. Now, this data is movement data. It contains references, pointers to other stuff, like what kind of schedule we have, location of that. They're not out there in clear. They're there in code. It is following the principle of normalization of like a database. I need reference data somehow to bring it in, and I need to join this data together. This reference data exists in two formats. One of them is just plain static data. Things like locations. A station doesn't tend to be moving around in the country unless there's an earthquake. So you typically have that in one single place. The train operating companies, well, occasionally one springs up or gets shut down by the government, but they don't change that often. So I put the stuff into my project in a CSV file. And then we have things that change potentially every day. Like a schedule, for example, that's been published by the National Rail to put in there. Turns out getting that data out was not quite as easy. So for the static data, I want to load the static data up into a topic so I can then simply join the topics together. There's no provisioning for that kind of thing in Terraform, of course. But I can do a bit of Java programming. So let me program something in Java. I built a little tool, the CSV file Avro uploader, that goes to the CSV file, finds the first header in the line on the top of that, creates a schema from that, and then reads the rest of the data and dumps it in that particular place using a generic Avro provider. So with that, I can simply gobble it up. When I access it via Terraform with a so-called null resource, it basically says, fire this up locally. It fires up the Java application, points it to the CSV file, eats it all in, dumps it into that topic, job done. Easy peasy, takes a few seconds. How about the irregular changing data? Well, they live, as it then turns out, on an S3 bucket somewhere in AWS. There's a nice web interface in front of it to pull it out. That web interface has been reasonably well built in the form that if you read the header of the web interface, it will tell you there is this file in here with the following name and the following timestamp. That's the last time it changed. They change once a day. So I can use this information to determine whether I have to load up the new schedule. I have a choice. I could do this with the deltas. That's a very small file. The problem with the deltas is they also contain delete, delete. And deleting things in KSQL is tricky. It involves tombstone and other bits and pieces, logic I didn't want to deal with. So I load the whole darn file. That turned out to be a compressed 2 GB beast. I have to download every single day. And I want to do this as a connector. That connector doesn't exist, I had to write it myself. A chance for me to learn how to write the connector, which, believe it or not, after 6 years of Confluent, I hadn't had done yet. Good. So it's a big gzip compressed file in JSON format. Each line is a JSON message that I have to process. I want to read it all in. It's 2 gigabytes uncompressed. Uncompressed, it's probably 3 or 4 times the size or something like this. If I do that all in memory, in a managed connector that I run in Confluent Cloud, that thing will simply blow up and tell me to go away because it has limited region for that, space for that, for the JVM. So it doesn't work this way. What I need to do is I need to treat it as a stream. Pull the data out, decompress it on the fly, read the individual lines, take those kind of things, dump them in, and then dump them out. And that's what this particular connector does. And keep track of where I am in the offsets of that connector, so that in case something goes wrong, I can go back to it again. So this thing exists here in my GitHub account. Writing connector itself, if you ever want to do that, you need to create a minimum of 3 classes. One of them is the kind of the declaration of the connector, the header, the metadata of that, and then there is a bit that keeps track of all the configuration files. If you want to configure the connector typically, which URL do I point to, which user permission do I have, and so on, these kind of things. And then I need the actual task itself that does the work, and there specifically I need the poll method. The poll method gets called by the connector framework, and then expected to return a list of source records in there, which happens to be the data itself plus the offset information that I want to keep track of where I am. Right, okay. I'm not going to show you the code of that. If you're interested, grab yourself the presentation afterwards or go to my GitHub account. You can find the code in there. And it's not that very complicated once you break. No, it's quite ugly because you have to keep track of state and when you keep the connection open and when you have to close the connection. So it is a bit trickier than the way I've talked about here, but it is not that tricky. If I can write it, then you can read it. More interesting for me, Terraform, in order to get that connector up and running. Yes, Confluent Cloud can take self-written connectors, connector plugin. And there's code in there that pulls this thing up. And then you can go and you can reference that and create the connector and run it actually. You have to provide a few parameters like which plugin am I using. You have to declare it as a custom connector and then you have to provide some endpoints. A custom connector cannot just willy-nilly go out and download stuff from anywhere. It actually needs to have a open firewall, so to speak, in that which you provide explicitly by giving it the endpoint connections in there. There turned to be 2. Because there's the front end that we are talk to, and that refers internally, or redirects internally to the S3 bucket to get the data out, and you have to put both of them in if you want to get this to run. And a few parameters in there, how many events do I create from this in blocks? That's basically how much memory I have for the connector available, and how often I try again every 5 minutes by default. I thought every 5 minutes to just create a quick HTTP connection to read the header. I think that's fair enough. I could do it every 24 hours because I know it only changes every 24 hours, but then I might miss a window. So 5 minutes was my compromise. Good. So we're done, right? That's so easy. Turns out the data we get in there is messy. Now that's why I wanted to have external data, because the data is messy. Real life data doesn't look nice and easy put together in that. They have all kinds of constraints and problems that they are built in. In this case, the good guys who built this data in there and dumped it active in queue followed a similar kind of principle as you would do with a Kafka producer. There's a buffer size, there's a linger time, waiting how long we wait until messages come in. We either fill the buffer or we time out, in which case we then take the buffer and write it out as a single JSON message, JSON array to be precise. So this block of data that I get has a bit of blah metadata on top of that. And then there's a big JSON array that contains a lot of line, headers and body, header and body in there for the individual messages. And I need to extract them. That turned to be tricky, certainly in KSQL. So here's a bit of KSQL code that actually does some of the extraction. The first thing is I dump it in a topic. I need to declare to KSQL that this is a stream, which I do with the creating stream on top of that. Doesn't do anything, it's just a declaration. And then I have to extract the actual field I'm interested in and turn it into within the Kafka world is in a single big string that contains all the JSON messages. And then I can dump a schema on top of that and pull it out and use the explode method to actually get the individual message out. So that's the exploder here down there. That's the magic trick that pulls this big block out and turns it into individual messages, which dump somewhere else. Now, if you follow through and look at that, you see that in order to process that, there are a couple more steps after this. I go through 5 different topics. Very expensive in and out. Just one of the many, many reasons why I want to migrate this to Flink, but Flink is fighting me on every single corner with this. We're slowly winning. So if you look at this thing in a few months, it will be written in Flink, and it will become much, much more simpler, and it doesn't consume so many resources anymore and other topics in between. But for now, that will do. There is one additional catch with this whole KSQL stuff. This pulls the initial JSON messages out and dumps it in there. I'll get to that in a moment. But first, let me explain what the data actually does. Messy data. Data with character. That's what we encounter in the real world. So it turns out all these movements around are actually not just movements. It's a state machine. The state machine starts with an activation. No train moves. Thank you. No train moves when unless I actually activate it. That can be done by a schedule or by some operator pressing a button or giving the train a good kick and said, move that way. So without activation, nothing moves. Then, hopefully, once it moves, it goes into this movement state and then moves around until it reaches its final destination. Unless something bad happens, like the train suddenly makes a jump, change of version, I have no idea why, or identity, that happens more often than you would think. It can be cancelled, it can be reinstated. All kinds of things can happen along the way. In the real case, which happens surprisingly rare, it just moves by itself. Now, the movement is what I'm after. For that to translate into something that human can read, I need to know the schedule and I need to know location. Unfortunately, they are not there. They are stored in the activation, which then refers to the schedule. I don't have direct access from the movement to the schedule. So I need to get this activation out. And if you look at the state and go, wait a moment, you just told me these are all in the same message box, you have to pull yourself like Munchausen by the top of the hair out of this thing. Yes, what's what I have to do? I have to read the activation information, dump them into a table to be looked up, then joined with the movements to find the actual schedule behind it, which tells me where the train is going. Which unfortunately means that the system itself has to run itself warm when it does. Because to begin with, the movements go, I can't find anything to join here because the table is empty. After a while, the activation table is still to fill up. And then if you go back again, you can find the movement. Then I'll link to the activation, which is linked to the schedule, and then I have closed the loop and actually have data in there. So if you ever try this out yourself, by all means, please do. Then just be aware that no data will come in for a while until about half an hour or so, until that system is up and running, and then it will run forever. So think about the KSQL statements. Uploading the KSQL statements, that's very nice, unless there's no Terraform provider for it. This has been not an oversight by the developers. By the time that they came around to actually building the KSQL statements in as a thing that you can talk to, Flink came around the corner and we basically decided to put our resources into Flink itself. So Flink statements I can easily put into my Terraform provider, and I'm just in the process of doing that. But KSQL can't. So out comes another Java application, in this case the KSQL Java client, that you can point to a directory full of KSQL text files, and then we'll load them up one by one and pull them in there. Good. Now, I promise I'll do this whole thing in half an hour. Last time I gave this talk, I was 1 hour talking, and then they had to physically drag me off the stage. So, you kind of get that I like to talk about this thing. But anyway, so I have achieved. I have a single Terraform script. Yes, there are some hacks in it, some extra Java libraries and other bits and pieces in there. Oh yeah, one point. This KSQL client in there, all my Java applications that are built, connectors and other stuff around it, they're all a few, maybe a megabyte in size or something like this. This KSQL piece downloads the half the internet. The underlying Java file that comes out of that, my first attempt, was 160 gigabytes, I think 160 megabytes. Now, what do you think the limit is on GitHub for uploading one single file?
I mean, they have large file storage now, right? But
I'll get to that in a second.
So you can hyper that.
So what's the limit on normal standard file in GitHub? 100 megabytes. So this thing's too big. Turns out I knew how to use my shadow library to pull the stuff out. Most of the stuff is not needed. So if you run it through a optimization stage, it then drops down to 80 megabytes or 85 megabytes and then easily works. So that's why downloading that GitHub repository takes a little while because the file is a lot larger there. Or you can build it yourself and put it in. Large file system. I used to work for Perforce, big version control system, which you probably never heard of because you're not working in the game industry or chip manufacturers. Every single chip and every single mobile phone, including the mobile phone itself, every single part of that is stored in a Perforce server. I'm not here to marketing for Perforce, I just spent 11 years there. So I'm a big fan of that. And I hate Git to vengeance. Now, I use it every day, but Git and large files don't fit together. Large file support is the most terrible thing ever created. In combination with GitHub, though, it is a wonderful source. Once you mark one single file as that, GitHub will go and say, oh, all these files have to be Git LFS. That'll cost you £100 a month. Pardon? What? There's my private accounts, free, everything is up there. Yeah, as soon as you put Git LFS support on, they want money, lots of money from you. So no. Anyway, but everything is in one single Terraform script. It pulls through. I didn't know Terraform before I joined Confluent. I've slowly learned it. This is my 4th or 5th project in Terraform. I'm a big fan of that tool. If you ever want to learn how to do this kind of stuff, it's not a bad place to start to look at it. You might laugh at my code, or you might find it interesting. I don't know, but it's a good place to start. And it's just all in the public repository. All this runs in the Confluent Cloud, one single place. I had a project in there running for over a year. It hasn't moved, it hasn't budged. Just connectors just keep running. Everything else just keeps running, filling out data, and then automatically fill up the other stuff behind it and so on. So whenever you want to actually do and connect some string applications to it and pull data out, there is your way to do it. Right. Finally, my one little marketing bit I was forced to put on. No, politely asked. You need the Confluent Cloud for this. You can get the free Confluent Cloud account, or free as in the starting point, $400 for free on top of that. If you want to play with Kafka, it's not a bad place to start. I poo-pooed that kind of thing. I've written part of the Kafka code. I've written some of the stuff, lots of deployment things around it and so on. The whole cloud thing was very much this is not for me, what is it good for? Got convinced about 2 years ago that that's exactly what it's good for, because click, and I have a running cluster and can start putting data in it. It is very quick and it is unbelievably useful. So if you have a project that you want to put in there, or you don't want to stamp up your own environment or own deployment, then that's not a bad way to go. Now off. Thank you very much. We have one question. Can we squeeze one question in?
Yeah, we got time for a couple of questions.
Yes, please.
I have like 3 questions, but
3 questions.
well, so what's
Pick your favorite.
so how long does it take from you push enter on your terminal to you have everything spun up? Not including the warm-up time that you take to actually populate your database.
About a minute, maybe 2.
Pretty good.
That's uploading all the stuff, getting connectors to work, and everything else in that. The topics are created in seconds. The hard part is to upload the reference data, and that takes a little bit while. Yeah. Next question.
So you talk a lot about build it up. How do you tear it down?
Terraform destroy,
It's simple.
which takes 5 to 10 seconds.
Yeah. Not bad. And then, so you talked a lot about, you sort of botched together a Java application because you need it because it doesn't support,
Certain
because
things.
you're building, because Confluent is focusing on these Flint or...
There's certain niche things in there, like, okay, when I uploaded this particular way,
So,
which you normally don't find this kind of way in there.
So my question is, after you migrate from KSQL to Flink, how much stuff will still need to be run through this Java application?
All the uploaders.
What?
All the data uploaders, they will still have to be run to that. And ActiveQ, of course, is a very big collector. I'm talking to engineering to see whether my compressed version, there's an HTTP source connector already, but none of them can deal with compressed data, and certainly not with 2 gigabyte files. So that needs a bit of trickery inside, and I'm trying to talk to them to get them to add this to the official list. Without much success, I have to say. The CSV uploader is, okay, it's a toy. And the KSQL uploader, hopefully I can get rid of by using standard Terraform. So there are a few bits and pieces in there, but the big chunk, which is that one, will hopefully go away. Any other question?
Sorry.
Okay, anyway, thank you.
Thank you very much.